Assalamu alaikum. I welcome everyone to our paper presentation in 2021 International Conference on Information and Communication Technology for Sustainable Development, ICICT for SD. Our paper ID is 155. Our paper is titled Application of Machine Learning for Optimal Placement of Distributed Generations. Here is a list of authors who contributed in this paper. Firstly, there is Shah Muazzam Hussain. He is from Department of ESE, MIST. Then myself, Mohammad Saif Hassan Onim from Department of ESE, MIST. Then Sagar Bishwas, Department of ESE, MIST. Finally, Abdul Hasib Chowdhury from Department of EEE, BUET. Here's outline. This is how we will be covering our whole presentation. Firstly, there is objective, then literature review, motivation, system model, mathematical formulation, probabilistic load, methodology, developed algorithm, result analysis, error analysis, conclusion, and references. Objective. Here are the objectives of our work. We focused on mainly these 3 points. Firstly, to develop an automatic technique for optimal placement of distribution generators by ensuring minimum power loss and maximum voltage improvement in power system networks. Secondly, to compare the performance analysis of KNN regression for predicting bus voltages. Finally, to minimize the computational complexities from traditional algorithm and replacing them with KNN, a machine learning algorithm. Literature review. Now, before we proceed to our work, let's look at some related work done previously in this field. As we can see from the table, in the year 2015, 16, and 17, several techniques were developed to optimize the power loss reductions. Firstly, there was network performance index, then particle swarm optimization, then analytical approach, and finally a software named Naplan. Then in the year 2014 and 16, they mainly focused on voltage profile improvement. They were namely immune algorithm and a software named Monte Carlo software. Finally, during the year throughout the year 2013 to 2018, several algorithms were proposed. They were mainly focused on both power loss reduction and also voltage profile improvement. All these algorithms were mainly implemented on maximum loading conditions. As you can see from both tables, they were implemented on maximum loading condition. So here we proposed a KNN based optimization technique for both power loss reduction and voltage profile improvement. And implemented this on time variant probabilistic loads, which is more practical in use, and the approach is also more viable. Now, why did we choose to work with time variant probabilistic load model instead of only the maximum loading conditions? As we know, loads may vary frequently from day to day, occasionally, and seasonally. So maximum loading condition is also a variant quantity. So proper loading can only be found with time varying load characteristics. So in this figure, one workday and another weekend are shown to give a brief idea of the data variation. These data were taken from Bangladesh Power Development Board, which again justifies our proposed methodology. Here we see the IEEE 14 bus system that we took as reference for our work to implement. Here bus 1 is the slack bus, bus 13, 14 is the PV bus. Now if we want to install a new DG, we will need to place the new DG in every possible bus and look for the change in related parameters. So to visualize this, this is what we're going to do. Now mathematical problem formulation. Here we define a function fx to optimize. It consists of an improved voltage change function and a power loss function. The optimization will be taking the maximum improved voltage function and minimum of the active power loss function. Generally, the bus voltage is calculated using the Gauss-Seidel iteration, allowing a certain range of error. So, and here's the equation for Vi. Next, similarly, active power loss is calculated. The equation is provided here. They were both implemented on a 2 single bus system network. Probabilistic load model. Now let's look at probabilistic load model. It is forecasted from the load variation data analysis of individual bus. For this type of loads, we focus on energy and power consumption. Power is calculated by energy consumed by the load in a year divided by total hours in a load. Here is a visualization of probabilistic load variations in the 13 buses throughout the year. Real and reactive powers are shown separately. Buses are indicated via a color. X-axis represents the hours and y-axis represents the magnitude. Now the traditional algorithm. It was according to this flowchart. Let me run it down briefly. Firstly, the new DG is inserted in a bus. Then three parameters are calculated parallelly: the reactive power loss, new bus voltage, and finally costing. These are iterated throughout all the buses until optimization is reached for each specific for the specific bus for which the criteria is obtained is our desired bus for the new DG insertion. The decisions were made based on a parameter lambda, where lambda is the priority multiplier. When lambda is kept at 50% or 33.33% for three parameters, they are all equally prioritized. This is the result for the traditional algorithm. For the final decision making, the table summarizes the change in voltage and the change in power loss, that is the voltage index and loss index. For bus 12, we can see the loss index is the lowest and the voltage index is the highest. So this met our desired criteria. So this will be the bus chosen for the new DG insertion. Now motivation. These are what exactly motivated us for our work. The first problem is the high computational complexities in the traditional method. Secondly, that was really time consuming. Thirdly, that cannot forecast the future data. So all this makes sure that it is less reliable. Now the methodology for KNN regression. This is a tool, machine learning tool that we've used for our forecasting part. As you can see, the KNN regressor is a statistical model where KNN stands for K Nearest Neighbours. It is a supervised learning algorithm, so we can train it under supervision. It is generally trained using level data that is called a dataset. The flowchart shows the training and predicting using the KNN algorithm. Here is what we did to improve the traditional algorithm. I will explain this block diagram briefly. Firstly, we took the bus voltage from last 10 years. Then after preprocessing, we used it to train the regression model. It was separately trained for the case of insertion of DG in each 13 buses. Then this trained model was used to predict the case for the 11th year. From this predicted data, the maximum increase in bus voltage was taken for further decision making. Similarly, in the below, we took the 10 year of previous data for loss, and we predicted the 11th year data for future forecasting. From this line loss, we found out the line with the lowest active power loss. Finally, the bus that supports both criteria, that is highest increase in voltage and lowest power loss, lowest active power loss, is selected for the final DG insertion. We implemented it on the same IEEE 14 bus network system so that we can compare the result between the traditional method and our KNN algorithm. In both cases, the final bus that was selected for DG insertion was the bus number 12. Here is the result. Here x-axis indicates the bus number and y-axis indicates the per unit voltage change. These are the comparative values for losses and voltage between both algorithms. Blue is the ground truth and red is the predicted value. This is for the voltage performance and this is for the loss. Here, this graph is an easier representation of our decision making. Blue represents the change in bus voltage and red represents the change in loss for all the buses from the previous condition without any DG. As, as bus 12 has the highest voltage with lowest power loss, it is selected for the DG insertion. Now, the result. Here is the prediction accuracy from the ground truth value, and as you can see, for most of the cases, the values are above 85%. Conclusion: the optimal placements leads to the increase in quality voltage profile, magnitude, and reduction in losses in a cost-effective manner. The developed algorithm is effective in interpreting the allocations of distributed generation for n number of candidates buses and generators. By using modern tools like machine learning, that reduces computational complexities and ensures fast response for this type of complex multivariable problems. These are the references we used in our work. Now again, thank you everyone. Thank you very much for listening to my presentation. If you have any question, I'll be here to answer them.